Hi, good morning students. So we are discussing about applications of the Gauss law. In that we started about studying the properties of conductors. So in the properties of conductor also in the last class we discussed about cavities and when the charges placed inside the cavity, how the charge distribution will take place, right? I hope all of you understood those concepts. And in the last class, I think in the last we discussed some problem based on the calculation like based on the induced charge distribution, like how to calculate the potential or fields due to induced charge distribution. So let us see some more problems based on that, and after that we will go to the next concept like concentric shells, right? And so in that, let us consider this a conducting sphere which is connected to the ground, that means which has an arrangement to connect to it to the ground through a switch. Now a point charge q is placed at a distance of x from the center here. So from the center its distance is x and the radius of this sphere is r. Now a point charge q is placed here. Now we need to calculate first of all when the switch is open, what is the potential due to the induced charge appearing on this. So in the last class we discussed already such a similar problem. Now let us see the continuation of that. So write that point, write that as a problem. A conducting sphere of radius r, a conducting sphere of radius r is connected to the ground through a switch S as shown in figure. Initially switch is open and a point charge q is placed at a distance x from the center of the neutral conducting sphere, at a distance x from the center of the neutral conducting sphere. So in that first question, find potential find charge flowing through the switch, when the switch S is closed, So that is the first question. And next question, the switch S is kept closed. Second question, this is in that the switch S is kept closed and the point charge Q is moving towards the center of the sphere, with constant velocity v. Then find rate of flow of charge through the switch. Rate of flow of charge in brackets actually that we define it as a current, and we will discuss that in the next class about the current. So that is the dq by dt, rate of flow of charge, that is nothing but actually we call that as a current. So find rate of flow of charge in brackets current flowing through the switch. Flowing through the switch means that is nothing but from ground to sphere or from sphere to ground. Some charge flow will take place there, right? And so now let us see. And actually about the grounding of the conductors we introduced it before only. That means at the when you are discussing about the potential, there only we discussed about the grounding. What will happen if you are grounding a conductor to the a conductor is connected to the ground. And there is now call it as grounding or earthing of the conductor. Simply the potential of the conductor will become zero, right? And so now here when you are closing it, now suppose this Q dash is the charge flowing to the switch and Q dash is the charge appearing on that I am assuming here. So mention that let Q dash be the charge flowing through the switch. Through the switch, yes. And so now here, now the potential at the center of this shell I am writing here. So potential of the sphere because we know it is a conducting, so we can write at any point. So generally we write at the center. So potential of the sphere I can write as potential at the center is equal to kq by x, that is potential due to this, plus kq dash by r, that is potential due to the charge flowing through the switch here. We are assuming some charge is flowing through this through the switch and it is residing on the surface of this conductor here, right? And so then due to that, when charge q dash is distributed there, then due to that it will be 0. And here one more potential is also there. Actually we need to write, that is nothing but potential due to the induced charge. When you are placing this charge at a distance, finite distance, there may be some charge induced on this, right? But in the previous problem, the last class, the last problem we discussed that the potential due to the induced charges on the surface of the sphere at the center will be 0. Because both positive and negative charges will be at the same distance. That means if this is the positive charge that is considered, then here then negative charge will be induced and this side positive charge will be induced. And so this negative charge and positive charge will are at the same distance r from the center of the sphere. And so potential due to positive charge will be kq by r and potential due to negative charge will be minus kq by r. So they cancel with each other. So that's why I am not writing the term there, right? And now this potential should be equal to 0. Why it is 0? Because the sphere is earthed. This sphere is connected to the ground through this conducting wire here, and so that value should be equal to 0. Therefore, from this q dash is equal to minus r into or r by x into q we can write here, right? So that is the charge flowing through the switch when it is closed and when it is kept at this point here. So this is our first problem. So this is the first part of our problem, right? And the second problem is given like it is moving with some velocity v here. That is the given information. The charge is, it is not at the fixed distance. Now this charge is moving with some velocity v and that is mentioned as a constant velocity there. And so then that is nothing but then automatically this term is variable here, right? Because potential due to that point charge is variable since this distance x is variable. And when this value is variable, then automatically this is also variable here. Q dash is also variable. Q dash is also variable in the sense continuously some flow of charge will take place here. That means the charge may increase or decrease depending on that. You can verify that. And so then some charge is flowing to this switch here, right? And so now here, that means here we are getting like if it is this is given as a positive charge. Finally the charge on this sphere must be negative charge. That is nothing but what we are getting here, right? So that means q dash is equal to minus r by x into q. So some negative charge is flowing from ground to this sphere. So that negative charge, finally the charge on the sphere will be a negative charge. And so now here, let us see the second problem here. The rate of flow of charge. So rate of flow of charge I can write as dq dash by dt. This is nothing but actually we call it as a current I. So dq dash by dt. Therefore this I is equal to minus q into r into d by dt of 1 by x. Means here I am going to differentiate this term here, q dash term. And so now qr is a constant that I am writing outside, then 1 by x term I am writing there. And so then you can write the differentiation of that 1 by x. And so it is minus qr into minus 1 by x square x power n formula into dx by dt, right? And therefore this value is nothing but QR by X square into V. So this is a current flowing here, because this V value is nothing but dx by dt you can write. The rate of flow of charge is nothing but you can write that as, that means that V value is nothing but velocity of this charge here. So velocity of the charge you can write as dx by dt. So that is our I value here. That is rate of flow of charge to this sphere from the ground to the sphere, right? So you can solve such a problems like that. So now let us see some more problems based on this. There is one theoretical question based on this here. This is Q, and small q is placed at the center of the sphere of radius r. And now from this, at a distance, some say smaller, another charge Q1 is placed at this outside here, right? This is a conducting shell. This is just a theoretical question. So now here the question is, when the charge, that means here the charge distribution is like, Q is the charge given to the conducting shell of radius r. This capital Q is the charge given to the conducting shell of radius r. And a point charge Q is placed, small q is placed at the center of the conducting shell. And another point charge Q1 is placed outside the shell. Outside the shell, that means it is placed at some distance is smaller. So this small r is greater than this r here. That means it is placed outside. So now our question is, so what is the force acting on this Q? That means here the question is like, find net force acting on Q. Find force acting on Q due to induced charges. That means first we need to discuss about net force acting on the Q, and due to the induced charges we need to consider here. That induced charges, or sometimes I will mention that as charge due to the sphere also. So charge due to the sphere is also, that means the force acting due to the sphere, not charge due to the sphere. So due to the sphere is nothing but induced charge, because the induced charge will be present on that sphere only. And so now let us see here. Here the assumption is all are positive only, all the charges are positive only. So when all the charges are positive, the force acting on this Q we need to find here, right? And so now if this charge is not there here, Q1 is not there here, then definitely easily we can say that the force acting on this Q1 will be 0, right? Because this charge will be distributed only on the outer surface, and so we know that electric field inside the shell will be 0. And so that no force will act on this. There is no field in the sense there is no force acting on this. And so net force acting on this will be 0. And next we need to discuss what is the effect of this Q1 here. What is the effect of this Q1 on Q? And in the last class we discussed this point also, like whenever you are placing some external charge, the effect of external charge on the cavities inside the conductor will be 0. Because the effect of this charge is cancelled by the induced charges appearing on the surface of the conductor. Like there in the cavities we discussed 2 points there. The effect of charges placed inside the cavities for external points, that effect will be. That means if suppose this is the cavity I am taking here, if you are placing a point charge here, then suppose if I ask a potential or the field at some external point there outside, then the effect of this charge for any external point is cancelled by the induced charge appearing on the surface here. We know on the surface minus q will be appearing, And so now the effect of these two charges will cancel with each other, either field or potential. Then only some charge will be induced on this outer surface here. Only that charge will produce that field or potential at that point, right? So that we already discussed it. Similarly, there we discussed one more reverse point also. A reverse point in the sense, if suppose this is a cavity here I am placing some charge here, right? Then what is field or potential at any point inside this due to that charge? So that means that also for any external charge, the electric field or potential, that means inside this, will be cancelled due to the induced charges appearing on this. That means due to this, one negative charge will be induced here and positive charge will be induced on the other side here, right? And so those two, the effect of this field and effect of induced charges, that means the field of induced charges will cancel with each other. And so that there is no any effect of this charge at any point inside this cavity here. So that we already discussed there. So now just we need to apply this point here. So based on that point, we can conclude that the net force acting on this Q due to this Q1 is also 0 because that is cancelled by the induced charges. And so the answer for the first point, first question is 0. There is no net force acting on this, right? And so we can conclude that net force acting on this will be 0. Net force acting on this Q placed at the center. I think you got the explanation. You understood that explanation, right? Next, find the force acting on Q due to the induced charges. So just now only we discussed that the net force acting on this Q is 0. So the net force acting on this is nothing but force due to Q1 plus force due to induced charges. These two will cancel with each other actually, right? Field due to the shell is this capital Q is already 0, so that we know already. There is no more discussion about that because field inside that shell will be 0, and so that we can conclude that there is no effect of the charge here, right? So only we are discussing the effect of this charge here. So now in this, the net force acting on this will be 0 because the external field cannot penetrate inside this conducting layer. That is nothing but we actually discussed it as electrostatic shielding also, right? And so now here actually how it becomes 0 means the electric field due to this charge and electric field due to induced charge, they will cancel with each other. And so I can write this as, so therefore this electric field due to the induced charge I can write as minus of electric field due to the Q1. And so now it is, therefore electric field due to the Q1 is, I can write this as, that means I will write the magnitude and I will write the direction. So K, Q, Q1 by, the distance is suppose say R square. And now its direction we can mention here, it's a direction, that means the force between these two will be repulsive since we are taking them as positive, so that will be towards left. And so now it will be towards right, you will get here. Towards Q1. Because induced charge force will be in opposite direction you will get. That means the force due to this charge will be towards left you will get, away from that Q1 you will get. Now force due to induced charge must be towards that Q1 which it should be. And so then that is the force acting on that there. So that is the force acting due to the induced charges calculations there, right? And now based on the force only, let us see one more problem here. That is in case of non-conducting shells. These are conducting shells, right? And so now let us see in case of non-conducting shells. So let us identify the difference between the conducting or non-conducting shells here. So now here this is say one conducting sphere of radius or having some charge Q, and this is another conducting, these are non-conducting, another non-conducting shell of say radius R and having some charge Q. such that their centers are separated by a distance of d, right? Now I am placing this another charge here. Another charge, say point charge q, is placed here at a distance of some small r from this, right? Now we need to calculate the force acting on this small q. So write that problem. Force acting on that small q, we need to calculate that. So write that problem. Two identical non-conducting spherical shells. So two identical non-conducting spherical shells, each of radius r. So this is non-conducting shell, and this is also. Two identical non-conducting shells, each of radius r, are having identical charge q each. Identical charge q each, distributed uniformly. Distributed uniformly. They are separated by a distance d. They are separated by a distance d, and a point charge q, small q, is placed inside one of the shell at a distance small r from the center, as shown in figure. At a distance small r from the center, as shown in the figure. Find force acting on the point charge q. Find force acting on the point charge q. So now let's see the calculation on this. So this I am writing like force acting on point charge q, right? So this force I am writing here. So this is force due to shell 1 plus force due to shell 2. This is suppose a first shell and this is second shell what we are taking. And here we are not taking any induced charges, because I mentioned this as a non-conducting, and so on this non-conducting there is no charge induced here, right? And so no charge is induced, and so that we can consider that as there is no effect of that induced charge. And so now only due to this shell 1 and shell 2 we need to calculate this force here. And due to this shell 1, the force due to shell 1 is 0, because the charge is inside the shell. And we know already inside the shell, either it is non-conducting or conducting, electric field will be 0 only, because the charge will be distributed only on the surface of the shell there. So in case of shell, whether it is conducting or non-conducting, the electric field inside the shell will be 0 only due to the charge on the surface there. And so that but field due to charge on the shell, field due to shell 1 at any point inside the shell is 0. Therefore, the force due to shell 1 is 0, right? So there is no force here. Therefore, I can write this as force due to this shell 2 only we need to write here. And therefore, the force due to shell 2 we can write as K into capital Q into small q by the distance I can consider it as some d minus r. The distance of the point charge from here. Simply you can write electric field at this point. So electric field at that point I can write as kq by r square. That means here r is nothing but d minus r whole square into that small q we can write here. So this is the force acting on this. So that is in case of such a non-conducting shells. So no need of considering such an induced effect. So directly you can calculate the force between them. So that is the force expressions there. Let us see some more problems based on these cavities here. Charge placed inside the cavities. So this, let us consider this. This is a conducting sphere now. Say conducting sphere of radius r, or let it be radius a, and in this some spherical cavity is there here. Now a point charge is placed at a distance of r from this. This is a point charge and this distance is r. Let's suppose this cavity radius is b. So this is a cavity. And so now we need to calculate electric field and potential at this point here. Set a distance of r from this r is greater than a, right? So at this point P we need to calculate electric field and potential. So at that point, write that problem. This is suppose say center C1 and this is C2. A point charge Q is placed at a distance r from the center of cavity spherical cavity of radius b inside radius b present inside a conducting sphere of radius a. The sphere is neutral. Then find electric field and potential at an external point P shown in figure. And also find second question, that is write it as a second question. Also find potential at the center of the cavity C2. A potential at the center of the cavity C2. And you may add one more point or write it as the next question. Find the total energy of the system. Yeah, we know, let us see now the solution for this. This charge is placed at this point here. So when the charge is placed at this point, we know some charge will be induced on this surface here. So minus q will be induced on the inner surface of this cavity, right? And as it is not at the center, we know the charge distribution is non-uniform. Non-uniform charge distribution will be there. But on the outside, this plus q will be induced here, right? I'm so sorry. This is plus q will be induced on the outer surface here. and which is a uniform distribution. Outer surface will be uniform distribution irrespective of location of the charge inside the cavity there. But we already discussed. And we also know that at the point P, the electric field or potential is produced by only charge on the surface of this outer surface here. So that means effect of this positive charge and negative charge will be cancelled there. So this is a positive charge placed at this at a distance r. So effect of either field or potential of this charge and this minus q induced charge will be cancelled for any external points there. Therefore, for external points, the electric field at point P is equal to, you can write this as simply kq by r square. And the field at point P, you can write this as kq by r. So that means only that external points means for external points, the field or potential is only due to the charge on the outer surface. Now let us write the potential at this center of this cavity here. This is the second question now. Potential at the center of cavity. That means at the point C2 we need to write. So potential at that point is nothing but, so I can write this as potential due to the plus Q, that means point charge, and potential due to the minus Q, that means induced charge, that is, and potential due to the Q. This means this is the outer surface and this is the surface of this cavity here. So that means those are the potentials we need to write at that point there, right? So potential at this point is nothing but the potential due to this point charge and the potential due to this induced charge and potential due to this outer surface we need to write, right? Or you can write that as potential due to the outer surface means the potential at this point, potential due to this charge and potential due to this charge. That means potential due to the charges inside the cavity plus potential at the center you can write. That will be the easy method. You can write the potential at the center due to other distribution of the charge, and so then potential due to these charges you can write there inside this cavity. So that gives a resultant potential at this point here. And so now the potential due to this point charge is nothing but I can write this as kq by r. So this also r and this also r is given. So I am taking this as some another distance here. So take this as, let it be simply r dash. And so that this distance will be r dash, you will get here r dash square, and this is also r dash. So this is kq by r and this is minus kq by b. This negative charge is distributed on the surface of this cavity there, so that you will get this as minus kq by b plus kq by this A, radius of the sphere you will get. That is nothing but potential due to this sphere. So that is nothing but potential at this center. You can write this as potential due to the charges, sum of the potential due to the charges inside the cavity plus potential at the center you need to write. If potential at the center is 0 for example, then this third term will be 0. So here there is some potential due to that charge also. So it is nothing but that potential you can write there. And so that is the calculation of this electric field at that point, electric potential at that point, right? And next this is a conducting sphere of radius say r, capital R, and a charge q is given to this, and it is having the two cavities now. So its radius is suppose say A, and here this q1 charge is present here, and its radius is suppose say B, and here at its center itself this q2 charge will be there. This is say center C1, and this is say C for example C1, C2, right? And now this is and this radius is suppose say R1, this distance is R1 and this is R. So now write the same, a similar question. We need to find the potential at these external points there. So write that a conducting sphere of radius radius r, a conducting sphere of radius r is having two spherical cavities, of radius a and b, as shown in the figure. A point charge q1 is placed inside the cavity at a distance r from the center, and another charge q2 is placed at the center of the second cavity. Another charge q2 is placed at the center of the second cavity. So first question in that, find electric field and potential at the external point P, and also second question, find the potential at the center of the first cavity, at the center C1 of the first cavity. And potential at the center of the second cavity C2. That means potential at the center of those two cavities we need to write there. So I think first part you can write here. That means here due to this minus q will be induced here, and so plus q1 will be induced here on the outer surface. So minus q2 will be induced here, and so plus q2 will be induced here. So that the charge on the outer surface will become q plus q1 plus q2, right? And so then potential at this point will be, we know, only due to this charge. And next, potential at the center C1 if you want to write. So similar to our previous problem, potential at this point is nothing but potential due to this point charge plus q1 and potential due to this minus q1 at the center, and potential at the center we need to write, or potential due to this outer surface, charge on the outer surface you can write there. And now potential due to this, these two charges will cancel with each other here, because the potential due to plus q2 and minus q2 will be cancelled there. So this is our minus q2, plus q2 will be there here. So then plus q2 and minus q2 will be cancelled at this point or at the center. So only this potential due to this charge you will get. And similarly, if you are writing potential at the center C2, if you are writing, that means what I am saying is, when you are writing potential at the center C1, only three terms are there. Potential due to this q1 plus q1 plus potential due to this minus q1 induced charge plus potential on the outer surface of this cavity. Only three terms. There is no need of considering these charges, because the effect of this minus q1 plus q will be cancelled for external point, right? For a external point of that cavity. Similarly, when you are writing potential at the center C2, Q2 is present at that point only, so no need of writing that Q2 term also. Then only potential due to this minus Q2 and potential due to this outer surface here, charges on the outer surface. Again, no need of considering these charges there. So like that you can write there. So then you can write those equations there, similar to that of our previous problem. So solve that problem. And the next here one more problem is there. So here again this is a spherical cavity of radius r. Sorry, this is a conducting sphere of radius r. Now here there is some cavity here. In this cavity, for example, I am placing a dipole. Plus Q and minus Q charge is placed here. Now our P is a point. Say at a distance of r from this. And it makes an angle theta with this. Right? And so now here we need to write potential at the point P and electric field at the point P we need to write here. So now in the previous questions, in the cavity questions, we are placing only one point charge there. Now we are placing a dipole. A dipole is placed here. Suppose say this length of this dipole is 2L. Right? And so now we need to write the potential at that point there. Potential at that point. So then write that question. In a spherical cavity of a conducting sphere, of radius r, a dipole is placed as shown in figure. Find electric field and potential at the point P due to the charges appearing on the outer surface of the sphere. Next question. Second question in that. Find electric potential at point P due to the inducer charges at point P. Is it? So now here, as it is a dipole is placed inside this cavity here, the charges will be induced on the surface of cavity. We already discussed what will happen when the dipole is placed inside the cavity, right? So then charges will be induced on the surface of this cavity here. Like near this positive charge, near this negative charge, some positive charge will be induced. On this side, near to this positive charge, some negative charge will be induced, such that net charge on this surface of the cavity will be equal to 0. So as the net charge on the cavity itself is 0, so there is no charge induced on the outer surface of the cavity, right? So when some net charge is inducing on the cavity, to balance that charge or to make the total charge of this object as 0 or the conducting sphere as 0, we know some charge is inducing on the outer surface here. But here inside the cavity or that means on the surface of cavity itself, the net charge is 0, right? And so that no charge will be induced on this outer surface here. So that means now charge induced on outer surface of cavity, outer surface of the sphere, not cavity, outer surface of sphere is 0. Therefore, electric potential, that means field at the point is 0 and potential at the point is 0. This is a net potential, net field and net potential at that point is 0, right? And then this is our first question here. Got it? Now the second question is about, they are asking that potential at point P due to the dipole they are asking there. So potential at the point P due to the dipole means you can write that as, due to the inducer charges. Right? Inducer charges appearing on surface of cavity they are asking there. So we derived an expression for this potential at any general point there. Suppose say this is our minus q and this is our plus q. Now the dipole is that means a point P for taking here such that this angle as an theta. Then we derived an expression like potential at that point P is nothing but due to this dipole will be equal to Kp cos theta by r square we can write if this distance is r, right? Now similarly we need to apply that formula here, right? And so if you apply that formula, and actually this angle is given as theta, and so now this angle will be total, when you compare this formula here, this theta is taken with this direction of the dipole here from negative to positive charge. And so now if you are taking that angle, then this total angle we need to write here. Suppose I am taking this total angle as some phi. And so now that phi is nothing but, here that phi is nothing but, so that means this is our formula. We are going to apply this formula. In this formula, this theta is nothing but this. So I will write that theta is also as phi, so that there is no confusion to you. So this angle I am taking as phi here, right? And so then Kp cos phi by r square you can write. So in our problem that phi is nothing but pi by 2 plus theta you can write. And now they are asking potential due to the induced charge at the point P. So therefore at point P we can write as potential at the point P is nothing but potential due to the dipole plus potential due to the induced charge. This induced charge is on the surface of cavity only. So this resultant potential should be equal to 0, so that there is no potential, any potential at that point here. The net potential at that point we are saying it as 0. These are nothing but net field. This field is nothing but net field, and this is also the net potential at that point there. So net potential at that point, right? And so that now here induced means where the charge is inducing only on the surface of this cavity here. So near this some positive charge will be induced there, and here this some negative charge will be induced there. So charges will induce only on the surface of this cavity. And now due to the dipole I am writing here. So due to the dipole I can write this as Kp cos of 90 plus theta pi by 2 plus theta by r square plus potential due to the induced charge. This value is equal to 0, right? Therefore, I can write this as potential due to the induced charge will be equal to, and here actually this value cos of 90 plus theta means minus you will get, and therefore we can write this as Kp cos theta by r square we can write. So that is the potential due to the induced charge at that point P. Induced charge on the surface of this cavity here. So these are some problems based on the cavities and the charges placed inside the cavity or outside the cavity. That means or in case of dipole. So these are some important problems based on this. So with the help of this knowledge, you can solve the problems based on this cavity. Any problem based on this cavity is there. And when you are placing the charges inside the cavity, either at the center or away from the center or outside the sphere, so you can solve all the problems based on these concepts there. So practice these problems thoroughly. Now I am going to the next model. Like the concept of concentric shells, and then based on that we can define the potential difference or a generator, Van de Graaff generator principle. Right. So now let us say this. So now first I am taking about I will explain the concept of concentric shells. And so now here in this, let us see first of all how the charge distribution will take place there. So we'll explain with some example here. So the first example I am taking here. So let us say these are two concentric spheres having some radius A and this is B, let us consider here, right? Or let us take this as A and B. So I will take the charge on this inner. So some charge Q is placed at this on the surface of the shell here. First shell. This is the first shell and this is the second shell we are considering here, right? I am giving the numbering here. So first and second. So now first let us discuss how the charge distribution will take place in case of the concentric shells. So in case of concentric shells, if suppose I am taking such a distribution, only charge is given to the inner shell and there is no charge on this outer shell here. We are not giving any charge to the outer shell. So write that point there. Consider the two concentric shells. Consider the two concentric shells. Two concentric and conducting shells. Those are conducting only. Conducting shells of radii A and B. Of radii A and B respectively as shown in figure. Respectively as shown in figure. Charge Q is given to the inner shell. Charge Q is given to the inner shell. And the outer shell is neutral. And the outer shell is neutral. Then the charge distribution on the different surfaces of the shells, charge distribution on the different surfaces of the, find charge distribution on the different surfaces of the shells. So let us take it as a problem so that you can solve this. And so here the first basic point here is we need to apply the Gauss law to consider the charge distributions there here, right? So first I am taking Gaussian surface. So this is considered a Gaussian surface. Inside shell A or shell 1, that means first shell we are taking that. So inside shell 1. So that means how this is inside the shell 1 means we consider like this. So that is a thin shell only. Inside this thin shell, just to represent a Gaussian surface, we are taking like this. So thin in the sense at the atomic level, it's some thickness will be there. So inside that we need to consider the Gaussian surface here. And this is the outer shell B will be there like this. So this is our radius A and this is the radius B. Got it? This is a charge Q we need to consider there, right? And so now is it clear why we are taking like this? That means we are taking a Gaussian surface. This is nothing but this shell only. To represent Gaussian surface inside the shell A, I am taking that as a two surfaces. Actually, practically these two surfaces are very close to each other. Inner and outer surface are very close to each other, so that the thickness of the shell is negligible. So to represent this Gaussian surface, I am taking like that. So now this is our Gaussian surface here. So the Gaussian surface. And so now you can write this as inside this shell, you can write this as now by Gauss law. So let us take this Gauss law here. A bar dot ds bar is equal to 1 by epsilon naught times charge enclosed. That means now actually what we are going to find is how this charge Q is distributed, whether the charge is inside or outside, that we are going to calculate here, right? So I am assuming some Q is a charge enclosed by this Gaussian surface here. And so now this point is, we already discussed many times, the Gaussian surface is inside the conductor we are taking, inside the conducting shell we are taking. Inside the conducting shell means then this value is 0 E value will be 0. So E is 0 in the sense, then you can write this value as, so that means, but inside conductor E is equal to 0. So therefore I can write this as 0 is equal to 1 by epsilon naught times charge enclosed. And that implies you can write this as charge enclosed is equal to 0. So right, that means no charge is present inside this shell, inner shell, except or provided no charge is present here. No, we are not placing any charge inside this. If you are placing any charge inside this, then some charge may be produced inside this. So that means if you are taking such a case here, no charge is present inside this shell, innermost shell, then charge only, this charge Q will be distributed only on its outer surface. So mention that as one of the fundamental point here. So mention that as one of the fundamental point. The charge given to the innermost shell only on its outer surface. Provided no other charges are placed inside it. Charges are placed inside it. So got it? That means when you are taking such a shell, initially in this problem we are taking some charge Q, right? We are giving some charge to this inner shell. Now what I am saying is that charge will be distributed only on this outer surface here. No charge is present on this inner surface of the innermost shell. You may consider any number of shells here. So then the charge given to the innermost shell, if you are giving any charge to the innermost shell, that will be distributed only on its outer surface, right? Provided no charge is placed here. If you are placing some charge, suppose say plus Q is there, then we need to apply for induced. Again Gauss law we need to consider here. From this Gauss law, inside this should be equal to 0. Then this Q plus some other Q dash should be equal to 0. From this you can write the Q dash is nothing but minus Q, which we discussed for the cavities. So then that problem will be similar to that of cavities. Then you can write this is plus Q, means here minus Q, and here plus Q we can write there. If any other charges are present. So if other charges are not there, then charge will be distributed only on its outer surface here. So this is one of the fundamental point, an important point, and this is true for any number of shells. For any number of shells, this point is valid. That means here only I am taking the 2 concentric shells. You may consider n number of concentric shells. So if you are giving some charge to Q to the innermost shell, and so that no point charges are placed inside it, then charge will be distributed only on its outer surface. That means up to now conclusion what we are getting is, inside this of radius A and this is the radius B, this charge will be distributed only on its outer surface here. So this is the conclusion we are getting here, right? So next we need to discuss about this. We need to discuss about the inner surface of this outermost shell, right? So again same, by taking Gauss law. So again let us take the Gauss law here. I think that point you can understand easily how the charge distribution will take place further. So now again consider the Gauss law, Gaussian surface inside the shell 2. Now let us take it inside the shell 2 here. Means this outer shell. Same, we are taking it as a some thick shell so that we can represent the Gaussian surface here. Actually, it is a thin shell only. And this is the innermost shell here having some charge Q distributed uniformly on its outer surface. So this is a plus Q. This is A and this is B. And this is our Gaussian surface. So again same calculation. So now let us apply here. So by Gauss law, here I am assuming some Q dash is a charge present here, or Q1 is a charge present on that. By Gauss law we can write this as phi is equal to integral of E bar dot ds bar is equal to 1 by epsilon naught times Q in. So again same reason, but inside the conducting sphere. So inside conductor E is equal to 0. Therefore this phi is equal to 0 is equal to 1 by epsilon naught times Q in. Now Q in means, now this is our Gaussian surface here. So inside this plus Q is there and Q1 is there. We are assuming that as some Q1. So I can write this as Q plus Q1 1 by epsilon naught times a Q plus Q1. And so that we can write this as Q1 plus Q is equal to 0. Or that implies you can write this as Q1 is equal to minus Q. Right? And so minus Q charge will be induced on the inner surface. This Q we are taking as the inner surface of this cavity here. So that means now an equal amount of opposite charges should be induced on the outer surface. Because it is the induced charges, we know induced charges always appear equal and opposite. On one surface, if minus Q induced, on the other surface, outer surface, the plus Q must be induced there. So that is another conclusion now here, right? And so now I can write this as so now the remaining shells, for any number of shells, now we can apply this point here. You can directly calculate like this. Therefore our conclusion is on the inner surface of outer shell, on the inner surface of outer shell, an equal amount of opposite to the net charge on inner shell will be induced, right? So that means now opposite, whatever the charge is there, if 10Q is there for example, then minus 10Q will be induced there. And so therefore we can finally conclude that charge distribution is, I am writing this charge distribution here. So now this charge distribution we can consider this as, so this is our innermost shell, this is the outer shell here, this is of radius A and this is a radius B, right? So the actually given charge distribution is plus Q is given to this sphere here. So that we concluded that plus Q will be distributed only on this outer surface. And so no charge is present inside this. And minus Q will be induced on the inner surface of this shell B, right? And so then an equal amount of, by the induction principles, we know that equal amount of opposite charge should be induced on the outer surface. And so then plus Q will be induced on its outer surface there, right? Therefore, we can write this as, now the charge densities I am writing here. for shell A, inner surface, that means I am writing in detail here charges on this shell A and shell B. For shell A, charge on inner surface is equal to 0. Charge on outer surface. Shell A is nothing but you may take it as a shell of radius A. This is outer surface is plus Q. For shell B, that means it is outer shell. Charge on inner surface is minus Q. Charge on outer surface is plus Q. So that now here itself we can discuss some more extensions for this. Extensions for this means if already some charge is there present on this outermost shell there. Suppose already some small q is given to this outermost shell. Then the total charge on the outer surface will become q plus q. So that here this is like or if you are taking like let us take like this is minus q and plus q, and if additionally already some charge q is present on this outermost shell, then it will become q plus q there, and there it doesn't affect the inner charge on the inner distribution here. Whatever the charge present on this outermost shell, I will discuss that as another example. This plus q given to the outermost shell doesn't affect the distribution of the innermost shells. I will discuss that as another example, right? So that means this is the thing we need to write. If already it is having some charge q, so this induced charge plus whatever the charge is there, that q we should write there. And similarly, if suppose for example, let us take this as a neutral only. If another third shell is also present here with zero charge, that means a neutral third shell is also present, then charge distribution means again we can follow the same principle. You can consider the Gaussian surface passing through this outermost shell, then net charge, these two will cancel with each other, plus q will be there, then minus q should be induced there. That means always you can remember that equal and opposite charge will be induced on this opposite surface here. That means this plus q is there, then minus q will be induced here, then plus q will be induced here. So this point we can remember it as a fundamental point. That means it is a conducting. All we are discussing as a conducting shells only. So for the conducting shells, the charges on the near surfaces must be equal and opposite. That means whether you are giving any charge to that shell or not, it doesn't depend. The charges on them will be whatever the charge is there on the inner shell, an equal amount of opposite charge will be present on the inner surface of the outer shell, that means next shell. Similarly, here it is plus q is there, then minus q will be induced here. So like that, whatever the charges are there, then equal and opposite charges will be induced on this. So I will give another example like what happens if the charge is given only to the outer surface of the shell, right? Then we can discuss in detail about these examples there, how the charge distribution will take place. So now write this as the next example then. Again we are taking the two concentric shells of radius A and radius B. Now I am giving the charge q to the only outer shell. I am giving the charge q to the only outer shell there. Now let us see what will happen, how the charge distribution will be there here. So then again we can conclude that when you are taking this Gaussian surface inside this, so there is no charge inside, and so that we can conclude that no charge is present inside this. And as a conductor is neutral, and so here charge is 0 and here also charge is 0. So that you can clearly identify that, right? Just similar to our previous, we can consider a Gaussian surface inside this. If you are taking a Gaussian surface inside this, then charge inside this will be 0 you will get by using that Gauss law. And charge inside is 0, then charge outside is also 0 because we are taking that inner shell as a neutral itself. We are taking that as a neutral only. And so now let us come to the next case here. The charge, again we consider the Gaussian surface inside this outer shell. So write that example. For the two concentric conducting shells shown in figure, the inner shell is neutral and outer shell is given charge q. Outer shell is given charge q. Then explain the charge distribution on the different surfaces. So by Gauss law, I am writing this now. By Gauss law, we can conclude that charge on inner surface of innermost shell. Charge on inner surface of innermost shell is 0. So this is nothing but our previous conclusion only. And so that here charge is 0, that is nothing but what I am mentioning there, and here also charge is 0, right? And as because here outside 0 I am saying that because this shell itself is a neutral. If any charge is present on that, that charge will be present on that surface here. If suppose say Q1 is a charge given to this, so that Q1 will reside on this outer surface there. And now let us write this about this outer shell. So for this I am taking Gaussian surface. So consider a Gaussian surface just inside shell B. Just inside the shell B. Right? So now this is our Gaussian surface. The dotted line is nothing but our Gaussian surface. And so now here we are taking some charge q is present on this inner shell here. This we already concluded. This is we discussed already. Q and q will be present on this surfaces there. Right? So now by Gauss law. So by Gauss law I can write integral of E bar dot ds bar is equal to dA bar or ds bar you can consider q in. And so now this term is 0. This we discussed many times. We are taking it inside the conductor, so the term is 0. So then this is 1 by epsilon naught times q. So therefore this q in is equal to 0 here. So no charge is present inside the on the inner surface of this outer shell, right? So that is our conclusion. Therefore the total charge given, therefore what we can conclude is total charge given to the outer shell distributes only on its outer surface. So therefore you can write this as the finally charge distribution I am writing here. So this is shell A and this is shell B I am taking here. Directly I am writing here, you may write separately. This is 0 and this is 0 and here also 0. Only plus q will be there on this outer surface here. For A, inner surface 0 outer surface 0, and for B, inner surface 0, outer surface Q. Means on the outer surface that plus Q will be distributed, on the inner surface it will be 0. So that is the charge distribution. That means now you can conclude that it is again true for any number of shells there. So that means if the charge is present only on the outer surface, it doesn't affect the charge distribution on the inner surface. That is why previously I said there. Like now let us take some extensions for this, or let us take some other examples for this. So now what I am saying here is the charge on the outer shell doesn't affect the distribution of the charge on the inner shell. So that you should note here. That means now here I am taking this, let us take this as a third example. So now this is having some charge Q1 and this is having some charge Q2, let us take here, right? And so now this is A and this is B. So first if you are able to write the charge distributions, then you can write the potential or field calculations or potential difference calculations there. So first I am explaining the charge distributions based on these concentric shells there, right? And so now if the charge distribution is like this, in the first example we discussed the charges present only on the inner surface. In the second example we discussed the charges present only on the outer surface. Now we are taking charges present on both the surfaces there, right? And so now the charge distribution. So I will write the charge distribution here separately. Just I am representing here so that you can write in detail. So this is a given condition here, right? All our conducting shells only we are taking here. So then the charge distribution will take place like this. So this is A and this is B. So then here it is 0, that we know already. Innermost surface of the inner shell will be 0, that means no charge will be distributed here. Then Q1 will be distributed here, right? And we discussed already that this is nothing but what I said here. The charge on the outermost shell, it doesn't influence or it doesn't affect the charge distribution on this inner shell here. So inner shell will take place whether it is neutral or whether charged shell is there. This distribution will take place as it is only. There is no effect. So Q1 will be there, and now because of this, now here charge will be induced here. So in the previous problem, here there is no charge, then automatically here also there is no charge here, right? But here when the charge is there here, then this also, then minus Q will be there here, minus Q1 will be there. On the outer surface, Q2 is there, in addition to that, plus Q1 will be there. Opposite to this, plus Q1 should be induced on this outer surface, that is plus Q1. Already Q2 is there on this outer surface. So the total charge will become Q1 plus Q2. Got it? So like that the charge distribution will take place there. For example, I am taking another example as a combination of 3 shells, let us consider there. So let us take this as a 3 shells. Combination of 3 concentric shells I am taking for example here. Right? So now let us take this as, this is A, B, and this is suppose say C, and this is Q minus 2Q plus 3Q. So these are the charges given to the shells here. Just let us write the charge distribution. I am not asking any potential or fields, just I am asking the charge distributions here, right? And so directly I am writing here with the help of our known points there. This is say one shell, and this is another shell, and this is a third shell I am taking here. For any number of shells, the procedure is same. We need to apply the same principles there here. So then here again the charge on this is A, B, let us take C. Charge on the inner surface of the innermost shell is 0. Next is plus Q will be distributed here. Then minus Q will be distributed here. Then it is minus 2Q plus Q will be there. Opposite to this, plus Q will be there. Already minus 2Q is there, so minus 2Q plus Q. So this will be net charge will be minus Q will be there on this outer surface. Got it? Now here the net charge is minus Q, and so then opposite to this here will be induced here. So that is plus Q, opposite to that. So plus Q will be induced on that surface. And now opposite to this again minus Q should be induced here. So minus Q plus already existing charge is 3Q. And so that the total charge will become 2Q. So these are the final charges on the different surfaces there. So 0 plus Q minus Q plus Q, and this is 2Q. And always remember this, on this these surfaces, these combination of surfaces, the charges are always equal and opposite, irrespective of the net charges given to these net charges given to those shells there. So it is a finding the charge distribution of the different cells in case of a concentric shells. So in the next class, I will explain how to find the potential difference and how to find the potential at different points and field at the different points due to this combination of the cells or a combination of concentric shells there. And we also discussed like one of the surfaces, one of the shell is grounded. In this, if one of the shell is grounded, how the charge distribution will take place. So like that, those points also we need to discuss there. So such a type of problems I will explain in the next class. Right? Thank you.